Hi, welcome back. Today we're going to discuss Euler's method. This is another way to approximate the value of a function. That's what Euler's does. This method does. It will approximate the value of a function. Now, it's going to look very familiar to us. It is basically tangent line, but instead of doing it in one step, we can do it in two or more steps to get even more accurate, better results. So let's take a look at an example. We're given the differential equation. So remember, here's our differential equation. Remember, this finds us slope. And then they give us some sort of initial condition right here. And what they want us to do is to be able to, from this condition, to approximate a value. And they're always going to tell you to use Euler's method and how many steps you're going to use. Equal steps meaning we're going to break the distance we're going to break our tangent line into two different parts. So we want to approximate the value of the function of y at point 8 using Euler's method with two equal steps. What this is saying is that we are going to use the tangent line twice. And then we're going to sketch our solution. So let's see here. I want to use a tangent line. So we're going to do this in two steps. So step one, are we having some fun? We need a point. Well, we need an initial point. And they give us that point, 0, 5. And I can plot that on my graph. If here's x, here's y. There's y. At 0, we're up at 5. We want to approximate the value at point 8. So I'll put that over here. Now, traditionally, we would find the equation of our tangent line at 5 and then plug in point 8. But Euler says, wait a minute. Let's not go all the way. Let's not plug in point 8 first. We're going to plug in a halfway point first. Pretty easy to do. So the first point they give us is this 0, 5. Well, from here, I can get the slope. That is just my derivative, and if I plug that in, that's just going to become 0 minus 2, which is negative 2. So my tangent line would be y minus 5 equals negative 2, x minus 0. Now here's where everything differs. And like we said, in a normal tangent line, we would just plug in 0.8 and be done with it. But starting at 0, we want to go two equal steps. So I'm going to go in between 0 and 0.8, 0.4. And I'm going to find this value first, x equals 0.4. Plugging in, we get y minus 5 equals negative 2, 0.4 minus 0, which is just 0.4. And you can solve this. This just becomes y is approximately, or in this case, I guess you just say equals, and this becomes 4.2. So at 0.4, we are now at the value 4.2. And I can kind of see, so that's what my tangent line would look like. Now remember, we didn't find the value at 0.8 yet, so we have to do another step. Step 2 is another tangent line. So again, I need a point. Well, I'm going to use my new point that I just found. 0.4, 4.2. And I'm going to do my tangent line again, so I got to find the slope. Again, this just comes from our derivative, dy dx, and that's going to be x minus 2 again, so 0.4 minus 2, and that becomes negative 1.6. So my second tangent line will be y minus 4.2 equals negative 1.6 times 0.4 minus 0. So we would get y minus 4.2. Whoops, sorry, that's terrible of me. That should be x minus 0.4. Somebody had already pointed that out already. Good for you. So this becomes y minus 4.2 equals negative 1.6. And now I'm going to plug in my new x value. Now I'm going to plug in my 0.8. We're going to let x equal 0.8. And if I let x be 0.8, we get 0.4 again. And solving, we get y minus 4.2 equals, and over here, we would get use my calculator. So let's go and use our calculator here. So we would go negative 1.6 times 0.4, and that becomes negative 0.64. And solving, we would get y equals 3.56. So we are approximating our value here, a y value of 3.56. And it's just another way to approximate our value. Now notice on our first one, the slope is negative 2. Here our slope is negative 1.6. These are two different lines right there. So, and then we can even ask ourselves, well, is this going to be increased? Is this going to be an overestimate or an underestimate? Well, from here we can look at our slope. So I can even test if this is an overestimate or an underestimate. Notice my slope is increasing. The slope goes from negative 2 to negative 1.6. This is increasing, therefore. So since we can say that f prime of x is increasing, our derivative, remember slope of the derivative, is increasing on the domain 0 to 0.8, f of x is concave up. Therefore, we have an underestimate. You might remember that from last semester. So we can even use this to help us find out if our answer going to be an overestimate or an underestimate. All right, so now for part B, it's a little bit different. Now part B says solve the differential equation for this solution for this and use it to find the actual value. So for part B, they want the actual value. That's what they're saying. So when they say solve it, now we're going to get the actual answer, and we'll see how far off we are in our approximation. So this is solving a differential. We've been doing this for a few days now. So solve, we get dy equals x minus 2 dx. Integrating both sides, we would get y equals x squared minus 2x plus c1. Use your initial condition. Now you could also use second FTC. We'll see that. I can show you that in a second here. So when I find C2, we're going to use a 0.05. We would get 5 equals 0 minus 0 plus C1. And C1 would equal 5. So our equation then would be y equals x squared minus 2x plus 5. And then I can just plug in the 0.8 right there. And if I plug that in, I'm going to use my trusty dusty calculator here. And that becomes 0.8 squared, right? This is 0.8 squared minus 2 times 0.8 plus 5. So 0.8 squared minus 2 times 0.8 plus 5, and we get 4.0. I was experiencing some technical difficulties. I forgot, when you take the derivative and the antiderivative, this should be over 2. So this is going to be x squared over 2, and that's going to be divided by 2. So when you find y of 0.8, we're going to get, if we type all that in our calculator now, let's try it again. We would get 0.8 squared divided by 2 minus 2 times 0.8 plus 5. And we get 3.72. And there's the actual value right there. Sorry about that. Now, mistakes happen like this. Don't stress mistakes. You just see me made a big mistake. But I kind of realized my answer was 3.56. I was getting 4.04 for an answer. And I know that can't be right because this is supposed to be a pretty close approximation. So I realized I made a mistake, and I went back and I found my error, and I had it fixed. So it's okay to make mistakes. Now, we could also do the second FTC here. All right? So the second FTC, you might, or the first fundamental theorem, FTC, first FTC on this problem. And that's just going to be our integral from 0 to 0.8 of our derivative, x minus 2 dx. I can do it here because everything is just in terms of x. And that's going to equal f of 0.8 minus f of 0. And we can just type that in our calculator. Let me go and grab my calculator, and if I integrate now, this won't work for every differential, but since it's just in terms of x, this will work out okay. Menu, for, limit, look for the integral, 3, and that's going to go from 0 to 0.8, and I'll type in x minus 2, don't forget the differential, dx. I press enter, and that's going to give us negative 1.28, and that's going to equal f of 0.8 minus f of 0, which is 5, and then adding f of 0.8, and if you add 5 to that, you get 3.72 again, and that's what we wanted right there. All right, so go to part 2, and we'll take a look at a few more examples. I'll see you then. Bye.